Okay, so welcome back to this morning's session, and it's my great pleasure and honor to announce the second speaker, Jean-Michel Raimond. He is professor at the Pierre and Marie Curie University in Paris and has been working most of his career with Rydberg atoms and cavity quantum electrodynamics. He's the father of many Schrödinger cats. And it turns out that he's also my thesis advisor, so I'm all the more happy to be here chairing this session and announcing your talk on quantum measurement and simulation with Rydberg atoms.
Thank you very much, Arno, and clearly being the thesis advisor of a chairman means that you are of age. So I'm very glad to be here. It's my time in Hong Kong and CTU, and I appreciate very much the warm welcome here and this event. So I will speak, not surprisingly, about quantum measurement, quantum simulation. I should mention that I'm also the PRX lead editor at APS, so if you have any private question about the publishing system, I would be ready to answer them later. So I think after the roundtable, I don't need a long introduction to tell you that quantum sensing and quantum simulation are some very important aspects of quantum information science. Quantum metrology, quantum measurement, if you will, quantum sensing, is how to harness the power of the quantum to improve the quality of the precision measurements that we can perform. And quantum simulation, we debated that a lot. I will only allude here to analog quantum simulation in the wording of Rainer. Quantum simulation, just finding the quantum system controllable enough to tell us something about complex quantum behaviors. And I would like to discuss these things, these great subjects in the context of Rydberg atoms. So quantum sensing, there are a variety of systems now that are used, quantum systems that are used to probe the environment. Basically, you can use one of the drawbacks of a quantum system, their high sensitivity to the external fields, to probe these external fields, and you can do that with ions, we can do that with NV centers, with Rydberg atoms, we already discussed that. But quantum-enabled sensing, quantum metrology, comes a bit farther than that and tries to use entanglement, tries to use non-classical quantum states to improve over the standard measurement. Very generally, the estimation of a physical quantity implies preparing your measuring device in some initial state psi naught, letting it evolve with an evolution that is controlled by the parameter you want to measure, and finally detecting the final state. And based on that, you want to estimate the value of a control parameter. If you do all this procedure with psi naught being a semi-classical state, for instance, for a field, it would be a current Glauber state, then you get a precision that is limited by the quantum fluctuations of this initial state psi naught, and we define what is called the standard quantum limit. But the standard quantum limit is not an absolute limit. You can get beyond that. You can get to a more fundamental limit, which I call the Heisenberg limit, by inputting in your system in a state that is non-classical. Let's discuss that in the frame of a spin, of a large spin. A large spin, as a spin 1/2, evolves on generalized Bloch sphere. Serge already discussed that in his talk yesterday. And imagine that you want to measure, you have a large spin in the magnetic field, you want to measure the magnetic field, so the quantity of interest is the rotation of the spin in the equatorial plane at a rate that is the Larmor frequency. If you prepare the spin in a spin current state that you obtain by a classical rotation from one of the poles, then you have quantum fluctuations of the spin that limit the precision with which you can measure the rotation of the spin and hence the magnetic field. This defines the standard quantum limit. But imagine now that instead of this semi-classical state, you could prepare squeeze state of the spin, as in these references, or that you can prepare a Schrödinger cat of the spin very much in the spirit of the Schrödinger cats of the quantum xenodynamics that Serge presented. You see that all these states have features that are much narrower than the dispersion of a classical state. So they are much more sensitive to variation of the magnetic field than the semi-classical state. This is the art of quantum metrology. Design the input state, be it a non-classical state and integer state, to get the best that you can get out of your measurement. Well, quantum simulation, I don't need to define that any longer. We discussed that at length in the round table. Basically, you want to understand a system that is too complex to be understood directly, for instance, and using ferromagnet with complex interactions. Then you mimic that with another quantum system that you can fully control, on which you have complete control of the experimental parameters. You can reach temperatures or magnetic field, which should be totally realistic in the real system. And then you can just measure everything on the system at the end of the evolution. And that's interesting only if you have something like 42 qubits, 42 being chosen not by chance, which is kind of the limit of what you can do by explicit diagonalization, explicit integration of a Schrödinger equation on a classical computer. And there are many instances of quantum simulation with trapped ions. We have seen that already with atomic lattices, with superconducting circuits, and with Rydberg atoms. And I would like so to discuss in this talk two experiments, basically. Well, one experiment and one project of an experiment. The experiment is about quantum electrometry and magnetometry using Schrödinger cat state with many quotes of Rydberg atoms. And the proposition to build a quantum simulator based on laser-trapped circular Rydberg atoms. And I will tell you why it could be more interesting than other features. So let's start with the electrometer and the magnetometer. You have heard from Serge Stoll that Rydberg atoms are blessed with quite remarkable properties. Those are states with a very high-lying principal quantum number n, of the order of 50 in everything we will discuss. They are very excited, but in spite of being very excited, they have extremely long lifetimes of the order of 100 microseconds for low L states that can be reached by laser excitation from the ground state, up to 30 milliseconds for the circular state corresponding to the maximum orbital and magnetic quantum numbers. The wave function of the circular state is a thin torus that is located around the classical Bohr orbit. One more application of the correspondence principle. You get back the classical results when all quantum numbers are large. These Rydberg atoms have very huge dipole matrix elements. Just because the size of the atom is enormous, the size is A0 n squared. So the size of an atom in the n equal 50 state is of the order of a quarter of a micron across. That's comparable to the size of a small bacteria or to a large virus. So they are extremely coupled to microwave fields, very sensitive to external electric fields, and they have also huge dipole interaction, and this is what we will use. But mostly they have an extremely rich level structure. In the manifold n equal 50, you have 2,500 levels, and here they are, all of them, for rubidium, in an electric field. We apply here on the rubidium electric field. This is computed, of course, and all the levels can be sorted by the values of m remaining a good quantum number in the cylindrical symmetry of the Stark effect. And you see that you have plenty of states with very different properties. The circular state with positive m is there. The circular state with negative m is there. There are two circular states corresponding to an electron orbiting in the two directions around the electric field that defines the quantization axis. Here, you have states with extremely large positive electric dipoles. It's not polarizability, it should be dipole. Here you have states with extremely large negative dipoles. So we have a combination of states which are impervious to electric fields and of states which are very sensitive to electric fields. But these states, circular states, are also very sensitive to magnetic field because they bear 50 units of angular momentum, 50 Bohr magnetons. And we will use that to probe at our choice, at our pleasure, either electric fields or magnetic fields. So let's look a bit more in detail into the structure, and let's forget about the quantum defect of rubidium, which makes the structure somewhat irregular here for low m values. And let's go to the hydrogen. everything is analytic, of course, and the Stark structure to first order is just this triangle of level with a circular level at the tip, m equals 0 there. All these levels are separated by transitions with exactly equal frequency, the Stark frequency, that is proportional to the electric field, and as an order of magnitude is the order of 100 megahertz in a field of 1 volt per centimeter. For n equal 50, I will stick to n equal 50 there, or 51, never mind. So you see that all these transitions are degenerate. So if you shine a radio frequency field on an atom, a radio frequency field that is resonant on the Stark transitions, then you excite at once all the transitions. And then you spread the population over the whole multiplicity of 2,500 levels. And you just get a mess. So it's not fun to get a mess. So we have, in fact, we have a very large scene to play quantum gates, but it's too large, we get lost. So we have to find a compass in that. And the compass is to use a pure sigma plus polarized RF field. If the polarization is very well controlled, you can only excite those transitions. If you start from the circular state, you can only go in the lower edge of this triangle. And this lower edge is a set of levels that are equally spaced and which exactly, it's one of the properties of the hydrogen atom, form a spin n over 2. So spin 25 in n equal 51. So we can isolate this manifold, a large spin, and we can play quantum gate with this large spin. The price to pay is to have a perfect controlled microwave radio frequency polarization. But that is easy with modern electronics. We just have a plain parallel condenser that sets the electric field. We have an atomic beam. We excite the atoms with lasers at a given time. Everything, of course, is time resolved. And around the condenser, we have 4 electrodes. And on those electrodes, we apply RF potentials. And by a very painstaking 1-month-long procedure, we tune the amplitude and the phase of all these electrodes to achieve here, near the center of the structure, an exact sigma plus polarization. When I mean exact, it means 99.9% or something like that. And so we can isolate the spin. And the first experiment you can do with a spin is just to rotate it. If you shine on the spin, for the Bloch sphere, the north pole will be the circular state, the south pole will be a low M laser excited state. If we start from the north pole, and if we shine a radio frequency which is resonant on the Stark transition, we will observe a rotation of the spin at some frequency. At any time, by this classical rotation, we will prepare a spin coherent state that is a superposition of states with different levels, with different M values. We have done this experiment, and we have published it recently. Serge, you have shown that, so you have already seen that. We just measure the probability to return to the circular state. We are initially in the south pole. We measure the probability to obtain the circular state, and we observe something like 20 rotations of the spin, which proves that we can really manipulate in a very coherent and very beautiful way this large spin. So let's now use that to measure the electric field. What about measuring the electric field? The electric field governs the spin intrinsic frequency. So it's just like the magnetic field if it was a magnetic spin. So basically, if you put the spin in the equator near Hong Kong, or well, we are not on the equator, we are somewhat north. Singapore, okay. Hong Kong is a bit north. But if you put the spin there, it will rotate around the z-axis at a frequency that is the Stark frequency. So if you can measure in a given interrogation time how much the spin rotates, it tells you what the electric field is. And the simple solution is then to go to Ramsey spectroscopy. You start from the North Pole, circular state. You flip the spin on the equator of the sphere. What I described apply as well to a spin 1/2 or to a large spin. You let the spin rotate for the interrogation time, and you put a second pi/2 radio frequency pulse, and you observe for which phase of the second pulse you return to the North Pole. And the phase the relative phase of the two RF pulse, the one that flips initially and the one that flips finally, just gives you how much the spin has rotated on the equator. So this is just the standard Ramsey method. And you have some interrogation time, of course. And here we did the experiment with our 25 spin, with two pulses, and for two electric fields that are separated by a very small increment of 500 microvolts per centimeter. It's admittedly a very small field increment. And what we observe is that we have a return probability to the upper state as a function of the relative phase of those two RF pulses. That is a Gaussian, which just reflects the quantum fluctuation of the spin current state. And the maximum tells us what the field is, and the width here is proportional to 1 over square root J, defining the standard quantum limit in this context. And obviously, we barely resolve here the field increment because the width, 1 over square root J, is much larger than the increment in the position. So how can we get further than that? So you see we have here a phase, that is this rotation phase, how much the spin rotates in the plane. But we have another phase that is hidden there. If a spin goes all the way on a path on a sphere, you have a geometrical phase, kind of Berry phase, if you wish, which is proportional to the area enclosed by the path on the sphere. If you could measure this phase, you would get something which is, of course, J times the spin length larger than the rotation on the equator. And that is the way maximum if you go down to the South Pole and up to the North Pole. So you could win a big factor on the phase measure. And so you could improve the sensitivity. But the point, of course, if you have a single spin, you cannot measure this phase. That is a global phase which is pertinent to one quantum system, so there is nothing to measure. But of course, we are not measuring a single spin. We are dealing with Rydberg atoms. We have plenty of levels in one manifold, and we have plenty of manifolds. So we can play a trick. Instead of using one spin, we will use two. We'll start in the, let's say, 50 manifold. And then with a microwave pulse in the circular state, we separate in a superposition of the 51 and 50 circular states. 51 lives with its spin, 50 lives with its spin. But the RF that is used to resonantly manipulate 51 is not resonant with 50, and the RF that manipulates 50 is not resonant with 51. So when you shine RF pulses which make the spin in the 50 manifold go over the Bloch sphere, the 51 state doesn't move. It behaves as a phase reference. So basically, you will do the evolution of the 50 state, put a phase on the n equal 50 manifold wave function, and then if you recombine the two 51 and 50 manifolds, you will get a Ramsey interference signal, a kind of nested Ramsey interference, in which you have microwave frequency and you have radio frequency to make those transformations, that will reveal the total phase accumulated by the 50 spin in its path on the Bloch sphere. And in fact, at one given time, you will have a superposition of a 51 circular state, which has no sensitivity to electric field, to first order, and on a state with a large dipole, which has a large sensitivity to electric field. You will prepare, this is an illustration of the wave functions that we actually prepare in the experiment, and you see they are radically different. Transiently, you have some sort of a Schrödinger cat of the atom, whatever it means. So this is the timing, pi over 2 microwave, pi large angle RF, pi over 2 microwave. And what do we get? So this was the signal we got in the classical version of the experiment. If we go quantum, and if we vary the phase between those two RF pulses, instead of wide Gaussians, we have a wide Gaussian envelope, and inside we have fast oscillations. And it's clear that the field increment between these curves, which is the same, is much more visible. It's even clearer if you go to scanning the microwave phase. There are plenty of phases in this experiment, I'm sorry, plenty of them, but if we scan microwave relative phase, we get Ramsey fringes, and we get a very clear distinction between the two sets of data corresponding to a small field increment. So we win over sensitivity. We win a factor square root of j. And we get at the end a sensitivity that scales like 1 over j, which is a general property of the Heisenberg limit. Louis has written beautiful papers on all that. So what is the sensitivity we get? This is the single-shot sensitivity. So the actual sensitivity you would get to discriminate two nearby fields would be that divided by the number of square root, the number of times you repeat the experiment. And this is what we get. As a function of the interrogation time, the sensitivity in millivolts per centimeter. This is the SQL, corresponding to the classical Ramsey experiment. This is the absolute Heisenberg limit that you cannot cross. These are the data we obtained in a recent paper that is in preparation. You see that we are very close to the Heisenberg limit for small interrogation times. For long interaction times, it's not as good. Why is it that? Just because our experiment is too good. For too long interaction time, we are sensitive to electric field fluctuations that we have not properly considered, mostly radio broadcasts in the Paris area. There's a lot of micro radio frequency broadcasts in Paris, and we do see that. We could get rid of that with a better screening of the experiment. What is interesting here is the lowest point. We get a sensitivity of 200 microvolts per centimeter in a 200 nanosecond interaction time. 200 microvolts per centimeter is the field of a single electron at a distance of 200 micrometers. So it means that with a small sample of Rydberg atoms, we could be able to detect the presence of a single electron at a 200 micrometer distance in only 200 nanoseconds. That compares and beats the most sensitive electrometers so far, including the single electron transistor. And the advantage of that, if you want, for instance, to use that to investigate mesoscopic physics devices, such as a carbon nanotube on which you can put a quantum dot. You want to know whether there's an electron there or not. You could just float some Rydberg atoms around, a couple of them, just to make a majority vote over whether the electron is there or not, and you could detect the presence of this electron in a time that compares well to the tunnel time that characterizes the transit of the electron in such structure. So there could be an interest for devices. Of course, here we measure the electric field in a short time, 200 nanoseconds. It means that we can also sample the evolution, like a sampling scope, the evolution of a time-varying electric field with a multi-megahertz bandwidth, provided the electric field that we sample can be synchronized with the experiment. And we did that, of course. But if you go to mesoscopic physics and, for instance, want to study the tunneling of electrons through a quantum dot, then there is no chance that you can synchronize the events. They are random. Is there a way to get information on a random, noisy, so to speak, electric field with that electrometer? And the answer is yes, by turning it into an AC quantum electrometer. So this is yet unpublished, but the general idea is the following. We just use the same nested Ramsey interferometer. One spin in 51 that does nothing, and the 50 manifold. But the 50 manifold, this time, I cannot describe it as a spin. Because I will first, at time t plus, make the same radio frequency excursion in the lower edge of the triangle to positive dipole states and back. And then at another time t minus, I will use a sigma minus polarized radio frequency field. All that is radio frequency, so all that can be triggered in real time. And I will go to rotation towards a large negative dipole state and back. And at the end of the day, the phase that you accumulate in that, it's easy to show that it's just the electric field at that time minus the electric field at that time. And so you get Ramsey phase that is just the difference of the electric fields. The difference of field is not fascinating, but this is a Ramsey phase. So imagine that you have a fluctuating signal with time, and you sample at two different times, and you plot the Ramsey interference pattern, the very same that I had here in this curve. So you plot the Ramsey interference pattern. Since f of t plus and f of t minus are two random variables, with some average plus fluctuations whose average is 0, the difference between the fluctuations there will result into a damping of the Ramsey contrast. It's a dephasing operation, so to speak. And it's easy to show that the contrast of the fringes is reduced by a factor which is written there. If you expand to first order in the phases, imagining that all the phases are small, you see that you get out of that a term that is the field correlation function, time correlation function. So this AC electrometer is able to directly measure a field time correlation function. And we have checked that in a variety of ways. For instance, we take a digitally generated noise that has a 1.5 microsecond correlation time. We set time interval to be much larger than the correlation. We just haven't correlated events. And we observe that if we increase the amplitude of the noise, the contrast decreases. And it does decrease exactly as predicted by this equation. The second order approximation being barely valid in that domain. If now we put the two interrogations closer in time, we do observe that the contrast, which is low at large time, becomes higher when the time comes smaller, directly measuring the field correlation. And the red dots are experimental. Here is the measure, is the known, because it's digitally synthesized noise. Here is the known correlation function of the electric field. And it fits perfectly well. So this is the same data for 0.5 microsecond correlation. And for white noise, we do observe that there is no contrast down to 0.0. So we are indeed able to measure directly the field correlation functions. So this is it as far as electric field is concerned. Now, can we use similar tricks to measure magnetic fields in a quantum-enabled way? And the answer is yes, of course. If we could prepare a quantum superposition of the two opposite circular states. It's a very weird system. It's an electron that orbits on a 0.25 micron diameter orbit, either in one way or in the other at the same time. So it's very Schrödinger cat-like. And if you put all the orders of magnitude, it's very well compared to a squid interfering device, by the way. This superposition is as those two states have 100 newbies of difference of magnetic momentum. So it's 100 times more sensitive to magnetic field than any standard rubidium atom. And at the same time, because of fundamental symmetries, those two states have exactly the same Stark effect, because the Stark effect is only dependent upon modulus of M, and hence they are absolutely insensitive to electric fields. So it's interesting to do that. I don't want to come into the details. It's a nightmarish experiment because you have to start from this state, which is laser accessible. You make a pi over 2 state to this state, a pi microwave pulse there, a pi radio frequency there, a circularization process in the 50 manifold, simultaneously a circularization process in the 52 manifold, and finally a microwave pulse to get back to the 50 manifold, and you have to do that with proper light shift to avoid unwanted transitions. So you have radio frequency fields everywhere. This is the time sequence that I don't want to discuss. Another difficulty of this experiment is, of course, that there is nothing to measure on the field ionization signal if you stop in the circular state. So the only way to measure something is to do the preparation of a superposition and to get back. And to measure the probability to get back to the initial state. So together it's 12 pulses RF of microwave and 4 adiabatic rapid passage preparations, multiphoton preparations. Okay, we have cheated a little bit, we stopped here. We have a little bit of sensitivity to Stark effect, but it avoids one step. And what we observe is something that is obviously sensitive to magnetic field, that is weakly sensitive to electric field, that is very sensitive to magnetic field. These are the Ramsey fringes that we get for a small field increment for 2 interrogation times. 20 microseconds, well, it's not very well chosen because it just corresponds to 2 pi increment of a phase, nearly to 2 pi increment of a phase. And we can From that deduce a sensitivity. We show that we are well below the standard quantum limit that we get in this context. And we have a sensitivity of 400 picotesla per square root of Hertz. Just by using longer interaction times with slower atoms, we could realistically get down to 4 picotesla per square root Hertz, making it most probably the most sensitive single atom magnetometer so far. So space and time resolved, and of course all that is time resolved. So it's also promising for fundamental applications. Okay, so the idea of all that was to use Schrödinger-Cat states, quantum superpositions of very different states, to achieve a higher sensitivity to electric or to magnetic field. In the first case, a superposition of states with radically different electric dipoles. In the second case, a superposition of states with radically different magnetic dipoles. Of course, these experiments, I must say, are proof of principle. To make that a practical commercial device, there is a long way to go. And we fully support that. I don't think we will embark in the whole way, but perhaps make a few little steps towards practical application of that. One of the key ideas being to get rid of the cryogenics, because cryogenics, all that is done at 4 Kelvin, and 4 Kelvin is a bit complex. So I would like now to change gears completely, and in the second part of this talk, to describe, it's merely a proposal now, but I think it's an interesting proposal which depicts the interest of Rydberg atoms at large and of circular states in particular, proposal for a quantum simulator, for a spin system quantum simulator. And this proposal is based on the dipole-dipole interaction between Rydberg atoms. Since Rydbergs have very large dipole, the dipole-dipole interaction is very large squared, because the two dipoles are large. And in fact, if you take just as an order of magnitude 260s Rydberg levels at a distance r, the interaction is a dipole-dipole van der Waals interaction C over r to the 6, and the order of magnitude is megahertz at a distance of a few microns. So it's really an extremely strong interaction. If you compare these few megahertz to the typical 20 kilohertz kinetic energy of a cold atomic cloud, you see that these interactions are enormous at the scale of the kinetic energies in that kind of system. So these interactions have been observed very, very long time ago. This is a very old paper that keeps being quoted. We did that with Serge in 36 years ago. Being of age. Yeah, okay, never mind. But this field is completely reviving with the advent of these techniques and with the interest of a quantum manipulation of this state. This dipole-dipole interaction has some very interesting consequences that are not directly I will use, but which are worth mentioning. The first is the dipole blockade, which was initially proposed by Michel Lukin, in 2001. And the dipole blockade is a very clever trick. Imagine that I have a pair of Rydberg atoms at a distance r. I can excite a pair of ground state atoms, sorry. I can excite one to the Rydberg state, either Rg or Gr. And those two states have no van der Waals interaction because the ground state is a tiny unpolarizable thing at the scale we are discussing now. But if I go to the two Rydbergs, then I have a van der Waals interaction, which depends strongly upon the interatomic distance. So imagine now that I shine a laser that is exactly at resonance with a transition between J, the ground state, and the Rydberg level. I can certainly excite one of the two atoms, but I cannot excite the second if the distance is low enough so that the shift, the van der Waals shift, is larger than the laser line width. So you cannot excite in a large sample of atoms. The first excited Rydberg atom defines a blockade sphere inside which there is no way you could excite a second atom. If the whole sample is smaller than the blockade radius, then you can excite only one atom in the Rydberg state out of a sample. It's a very clever way to restrict to the 0-1 basis something that would not be restricted in the absence of a dipole blockade. Of course, that holds if the laser is at resonance with the displaced transition. If you tune the laser on the blue, this is the case of a repulsive interaction, you tune the laser to the blue, you see that you get at resonance or a two-photon transition when the distance between the atoms is such that the van der Waals interaction exactly compensates the detuning. So it means that in the detuned case, you excite the first atom there by chance on the wings of the transition. The second will be excited, preferably at some distance, a facilitation radius that is well defined. And many people are working on that because it has all kinds of very interesting properties. You can build quantum gates out of that. You can build plenty of things. And you can build, in principle, quantum simulators. Why is it that? The quantum excitation of a gas of atom is a many-body problem in which there is a kind of antiferromagnetic in the dipole blockade regime of antiferromagnetic interaction between the atoms that will be excited. They cannot be excited close together. And so there has been very beautiful experiments, particularly a beautiful preprint by Misha Lukin with 51 atoms. And so there are many teams that embarked in quantum simulation with Rydberg atoms. Many body problems. It's fine, the interactions are huge, it's easy to detect the atoms. It has many advantages, but there is one main drawback. If you want to make a quantum simulation that runs for a long time, that studies long time processes, like the kind of process you have in spin glass dynamics, like the kind of process you have in many-body localization effects when you have disorder, then you need to follow the evolution over long times. Those Rydberg atoms interact strongly, but they also, laser-accessible ones, have a short lifetime, 100 microseconds, and an even shorter lifetime if you operate in a room temperature environment, few microseconds only. So you have a finite lifetime. Another big problem is atomic motion. As I told you, van der Waals interaction is huge, which means that if you have two atoms nearby, their potential energy is thousands of times their kinetic energy. So they just fly apart. The atomic sample explodes with a dynamical time constant of the order of a microsecond. So there is no way by which you could simulate more than a couple of microseconds, so more than a couple of characteristic interaction times. You can reduce that by dressing the ground state with Rydberg character, but it doesn't completely resolve the problem, I would say. And so the idea is to operate with long-lived Rydberg atoms, and moreover, in all these experiments, the Rydberg atoms are not trapped, just free. You start with trapped ground state, you go to the Rydberg state, and then the atom is free, because the Rydberg state is quite impervious, seemingly, to lasers. So can we trap the Rydberg atoms? Can we extend their lifetime enough to go into very long time range? And the answer is yes, if you go to circular Rydberg states. So once again, the circular Rydberg state, we've seen that, it has been our workhorse for 30 years in cavity QED exploration. They are long-lived, 25 milliseconds for 48C, 30 milliseconds for 50C. So it's decently long-lived, but it's not enough. We are more ambitious than that. How can we make it longer-lived even? And then we can transpose an idea that was put forth by Dan Kleppner in 81 and demonstrated together with Randy Hewlett in 85, that is spontaneous emission inhibition. The Rydberg state, the circular Rydberg states, due to selection rules, can only decay by spontaneous emission of the microwave transition towards the next lower circular Rydberg state. And so the lifetime is just a cascade from the circular state down to the ground state. But this first step of emission is sigma plus polarized, and this first step of emission is microwave. So you can just prevent that emission from occurring by placing the atom in a structure in which this microwave cannot exist. And the structure is certainly simple. It's just a plain parallel capacitor with a spacing within the plane that is shorter than half the radiated wavelength. This is exactly what Kleppner demonstrated a long time ago. And we have made some simulations of that. Of course, you need to take into account realistic effect. The suppression is perfect for an infinite capacitor. You have to take into account that the capacitor will be finite. You need to shine laser on the atoms, that the capacitor will have a finite conductivity. So you pay a lot to have a good microwave computing studio, and you compute the spontaneous emission rate. And you have to take into account also the fact that at the end we will have interacting atoms. And when two atoms interact, there is a mixing of a circular state with other states which can decay. And you have to take into account the fact that there is black body that you can absorb. Going to higher levels, you have no inhibition because of polarization. At the end of the day, you get that a pair of Rydberg atoms interacting at a 5 micron distance could have, in very realistic setting, a lifetime of a minute. So we were speaking of the eternal qubit in Rainer's talk yesterday. It's not eternal. There is nothing that is eternal. And even if there were, I would not be able to check it. I'm not eternal myself, at least I think. But certainly we can extend the lifetime of a Rydberg atom in the domain of the order of a minute. That is infinitely long at the time of a standard interaction. Of course, if you want to extend that in the domain of a minute, then you need to trap. Because in a minute, the atoms would fall by at least the half of one of the towers in Hong Kong. So there is no way by which you could build that. And the good news is that circular states can be laser trapped. Why is it that? Because a circular state is basically viewed from a laser's perspective. It's a free electron. And a free electron in a laser feels an energy, a ponderomotive energy, that is proportional to the intensity of the beam. So the Rydberg atom as a whole feels this ponderomotive energy and seeks the places where the field intensity is minimum. So it's a low field seeker. So you can trap in a shallow trap, in a minimum, local minimum of a laser intensity field. And it's quite a deep trap. In fact, a free electron is at 1 micrometer wavelength 10 times more polarizable than a rubidium atom at the same wavelength. So it's a very deep trap, very easy. And of course, all techniques of laser trapping, that I don't know that I know very little about, can be transposed. Another good thing is that the ponderomotive energy only depends upon the electron characteristics. It doesn't depend upon the principal quantum number to first order. Okay. But so it's a state-insensitive trap, which is excellent because it means that the coherence of a qubit could be kept for a long time. Of course, you will jump on me saying, but obviously the atom will photoionize. This is certainly true for low L states. It has been shown, Safman had made experiments on that. They photoionize in a 1 watt typical laser trap. They photoionize in a time of tens of nanoseconds. But the circular state has a very specific property. How can you photoionize an electron? You need the electron to have a momentum that is on a par with the momentum it will have when released. So to have a momentum which is of the order of the momentum of a photon. And that occurs when the electron is at a distance from the nucleus that is of the order of a Bohr radius, just by dimensional analysis. And in the circular state, the electron never comes close to the radius. So it never has the momentum that would allow him to be ionized. And of course, there is an explicit calculation. This is all hydrogenic. And you get that in a 1 watt on 1 micrometer laser field, the lifetime of a circular atom, n equal 50, is 10 to the 175 seconds. I guess the calculation is wrong, but 10 to the 175 seconds is a long, long time. It's much longer than the age of the universe. So it could work. And this is a splendid feature of a Rydberg atom. And if we take into account everything, we slightly reduce various Compton diffusion via free electron that causes level change, but this is weak. We still are in the minute range for trapped atoms. So the trap geometry would be very simple. It's just a donut beam with a minimum on the axis that defines a longitudinal confinement along the axis, and a standing wave pattern that we use by interfering two beams at a shallow angle, just to get a spacing between the lattice sides that is of the order of a few microns, say between 5 and 7, this is the right range, to take benefit of the van der Waals interaction. And the longitudinal oscillation frequency should be in the tens of kilohertz range, so should be a rather high frequency. It's very tight trap indeed, which is good news. Now, the idea is to have, obviously, a chain of Rydberg atoms in the lattice, and to implement a spin Hamiltonian on this lattice. So what is the interaction? First, let's choose the levels. If we take all the atoms in the same level, nothing happens, so it's not fair. Imagine that we take 50C to implement the spin-up state and 49C to implement the spin-down state. Then we have two types of interactions. We have a diagonal van der Waals interaction between two atoms in 40, in 50, two atoms in 49. And we have also, if we have one in 49 and one in 50, an exchange interaction in which the two atoms swap their energy. This exchange interaction, because it's resonant, is on the first order in the dipole-dipole coupling. So it's just like 1 over r cubed instead of a direct interaction, which is 1 over r6. And it's overwhelming the van der Waals interaction. So it's no good choice. The good choice instead is to code the two spins on 48C and 50C, connected by a two-photon transition. Then both the direct van der Waals interaction and the exchange interaction vary like 1 over r6 and are of the same order of magnitude. And you can compute that, just diagonalize the complete Hamiltonian of two atoms with the electric field. You need a magnetic field with a magnetic field as well, and all of the perturbations, and brute force compute, and you get what the interaction is. At the end of the day also, and similar thing applies to the ions, of course. If you have 48, which is spin down, and 50, which is spin up, it's clear that the ground state is all atoms in 48. Because there is a huge energy, 130 gigahertz, between the two levels. So if you want something a bit funny to appear, you need to dress the atom with a nearly resonant microwave that mixes level 48 and 50. And if you work out everything, you get at the end that the Hamiltonian of the chain is that. There are many terms in that. There is a term here that is a Z term, that is just where that is just the detuning of the source. There is a dressing that is come to the X term. All that, these are the Pauli matrices of the diverse atoms. And then you have coupling terms. You have an exchange term, XX plus YY, which you can recast as sigma plus sigma minus plus sigma minus sigma plus, obviously, which describes the exchange. And J here is the term that will define the time unit in our Hamiltonian. And then you have a ZZ interaction. And that is called an XXZ model in transverse fields. And it seems to be a very popular model in spins and be a favorite workhorse of theoreticians in that domain. What are the orders of magnitude? At 5 micrometer distance, G is 17 kilohertz, the exchange rate, meaning a 10 microsecond exchange period. There is a factor 4 because it's polymatrices and not spins. So there is a 100 kilohertz exchange frequency. We can trap a chain of atoms, say 42 atoms. The lifetime of the atom is 42 seconds. So we have something like a 1 second lifetime for a chain, which is about 10 to the 5 spin exchange times. And this is infinitely more than what has been achieved so far in the current term of simulators. Another very important thing is that all the parameters of the Hamiltonian are under experimental control. Delta and omega, the transverse field, it's very clear. It's a microwave frequency. You can just tune it in real time as you wish. But JZ can also be tuned. Because the atom is placed in an electric field. It's also placed in a magnetic field. You need both to really stabilize the circular orbit. And if you compute JZ as over J as a function of F for various values of B, you find that it depends very rapidly upon the electric field. J is basically invariant, the exchange term, doesn't change, but JZ changes a lot. It's because you have kind of Foster processes when pair states coupled to the circular states get in or out of resonance with in the van der Waals second order expansion. So you can tune that just by tuning an electric and a magnetic field, or just by tuning an electric field. Magnetic field is slow. So you can change in this Hamiltonian you can change all the terms, sorry, I will succeed, you can change all the terms over a time scale. This is invariant, of course, this is the time you need. You can change all these terms in a time scale that is much smaller than G, which opens many possibilities for instance, flow-state engineering. Okay, why should we change that? Because the phase diagram of that is extremely rich. So this is a phase diagram that has been derived from that publication and that we have supported by explicit matrix product state simulations, calculations of the ground state of the system. You have for, this is in the case delta equals 0 as a function of omega and jz over j. You have a paramagnetic phase where basically all atoms are polarized along x. You have a ferromagnetic phase, they are all along z. And there is two Néel phases ordered with a staggered order, either along x or j. And there are plenty of things that I don't understand absolutely about this phase diagram. But it seems that spin chain specialists understand better than I, but very interesting points in this phase diagram. And this is a matrix product state calculation of a ground state for 40 atoms. And you see that already for 40 atoms, we are close to a thermodynamic limit because what we observe for various orders parameters that I don't want to describe in detail is very close to the phase diagram. So it sets interesting perspective for this simulator. Of course, the key requirement in all that is that we should be able to prepare a defect-free chain of circular Rydberg atoms. Exactly one Rydberg atom per lattice site. No more, no less. You can very easily, in atomic lattices techniques, prepare one atom per site in the mode blockade, in the mode insulator regime, in the Fermi regime. But there is no way by which you could, with certainty, put 40 of these atoms exactly in the circular state. So we need something else, and we have defined a funny method which is basically a van der Waals version of the evaporative cooling. And the idea is very simple. We trap some Rydberg atoms, randomly ordered, in this laser tube. So it's basically a 1D chain, completely disordered. But we put two plugs at the end of the tube, two laser beams that act as plug. And then we compress. And one plug is hard, the other plug is weak. When we compress, we squeeze the atom together, their mutual interaction energy increases up to the point where the last atom is ejected above the weakest barrier. And since it's ejected, it provides some sort of cooling of the motion, because it takes a bit of the energy off. And then we compress, and we have shown by explicit numerical simulation of the dynamics, classical dynamics, that the number of atoms, sorry, I should use that the number of atoms remaining in the chain is a function of the distance between the two plugs with very clear steps over which we prepare an exact number of atoms inside the chain. And this numerical simulation, classical, say that the mean number of quanta in vibration, the final lattice that we install at the end of the procedure, is close to 1. So it means that the classical simulations are not adapted, but there is some sort of cooling there. And so it's a very efficient way of preparing that. Another important point is that the same method can be used to detect the atoms. When we have let the spin chain evolve for a time, we just stop the interaction by casting, for instance, 48C over 46, and 46 and 50, there is no longer any exchange interaction. So we freeze the atomic state, and we just resume the evaporation. And we eject the atoms one out of a time out of a chain at a controllable rate, and we eject them at a 2 meters per second velocity towards the detector in which we can detect their states. So we can measure with additional microwave rotations, we can a priori test any observable on all the atoms and measure any correlation function. Well, the experiment would be long, but that's the problem with students. So there are plenty of things you can study with that. Obviously, studying the phase diagram is no use because the MPS techniques provide you the answer. So the phase diagram should be used as a benchmark of a quantum simulator. Once again, it's very hard to check that a quantum simulator simulates what it is designed for, but the phase diagram is a good benchmark. But then we could get to more complex dynamics, such as sudden quenches through the phase diagram, in which the resulting state involves a large number of excited states in the new parameter range, and for which direct computations are difficult. And you can make that very much more complex. You can think of putting disorder by adding a laser speckled field to the traps. You can even think, using techniques derived from Lukins or Borway's techniques, to have 50 or 100 independent tweezer trap manipulating independently 100 Rydberg atoms for a minute and moving them around over a few microns at a 10 kilohertz rate, which is of the order of a trapping frequency. And so tailoring in real time, trotterizing basically arbitrary interactions of a speed. So we believe it's important and need to build that. I only wish the French government would have the same funding policy as the Hong Kong one. But that's another story. So this is the group. So this is a group photo. So there are permanent members, Serge Haroche, you might know him, Michel Brune, and we have worked all three together for now 30 years, something like that. Sébastien Glaise, who is there, hidden there. Igor Dotsenko, who is there. And Clément Serrin, who turns out not to be in this picture, I'm very sorry for that, who will be in charge of this experiment. And we have collaborated for the theory part with Thierry Jolicoeur and Guillaume Roux from LPTMS in Orsay, who provided us with the MPS techniques that we clearly don't master. And these are all the students working on our experiments. So thank you very much for your attention, and I look forward to your questions.
Thank you very much, Jean-Michel, for this fascinating talk. So the paper is open for questions. Dave.
Jean-Michel, being an ion trapper, what I want to think about is that you're putting this circular atom in this laser trapping field, right? But so is it right to think you're basically just trapping the electron in this optical potential, and the core is attached to the
core follows, yes.
Yeah, okay.
Yeah. This trapping, I should have mentioned, I think I had the reference, was proposed in 2001 by Georg Reitel.
Say again?
Georg Reitel
Yeah.
proposed this trapping technique in 2001.
I see.
I don't think he has yet implemented it, but well, the algebra seems to be there, and the orders of magnitude seem to be there. What we are doing right now is trying to trap a circular Rydberg atom just for a couple of milliseconds, just to check that it works.
But anyway, and maybe you said it, but in your simulations, then what I would call the micromotion is not a big perturbation on the dynamics?
The micromotion corresponds to about one oscillation quanta in the final lattice, and certainly we should make a quantum model of the evaporative cooling, but that's very hard, and I don't know how to make that. Well, for 2 atoms perhaps, but that's very hard. That's a problem for Yvan Castin and other guys. What we observe, of course, there is a motion. Of course, the motion modulates the J coefficient, and that's bad. That's very bad, as someone says repeatedly. What we have observed is that you can sort that out by diminishing slightly the J coefficient, that going to the 7 micron distance, so that J is typically 1 order of magnitude less than the trapping frequency. And in that case, the trapping, basically the interaction is averaged out. And we have made the exact numerical diagonalization approach to quench a slow adiabatic evolution with the motion put in the thing. So it's a huge calculation on a cluster. For 14 atoms, there is no way you could go to 15. And at the end of the day, we observe that with 9, for instance, we make a transition through phase transition, and we come back, and we return to the initial state with a 9.9995 fidelity. So motion doesn't seem to be a problem in that regime. Of course, it's the question the referee asked when we submitted the paper, so you might be the referee. But it's a very good question, obviously.
Okay, so Christophe has another question.
I missed it. What is the kind of light shift that you want to apply actually to make the system degenerate? You said that the 48 and 50.
Oh, it's not a light shift. It's just a resonant microwave drive.
Yes, and what does it do then? It prepares...
It makes that the two eigenstates with this drive are just 49 plus 50 and 49 minus 50.
Okay.
And it just equalizes the energy of the two states.
Yes, okay, that's the omega term.
Yeah, that's the omega
sigma
term.
x.
That's the omega term.
Okay.
More questions? Maybe I can ask one question about the assumptions concerning the damping of your superconducting, I mean the electrical damping of the superconductors in the presence of your trapping light, because I have been collaborating with people from JQI and they were scared of less than picowatts impinging on their superconductors.
Well, first, we will work at a decent temperature of 0.4 K. And second, the condenser needs not be superconducting, must not be superconducting. It will just be gold. Gold at 0.5 K is not superconducting, but it's still a very, very, very good conductor.
Okay,
And
so
for spontaneous inhibition, you don't need, well, if you take in terms of finesse of a Fabry-Perot cavity, superconductor reaches, as we've shown, in the 10 to the 10 range. To inhibit spontaneous emission by 50 dB, you need a Q of a finesse of 10 to the 5.
Okay.
And gold has a finesse of 10 to the 5 at those temperatures. So it will just be gold because we need a magnetic field. And why do we need a magnetic field? That's very technical. To remove in the Stark manifold the degeneracy of the circular state with the elliptical states which have just second order Stark effect. And then to remove that degeneracy, we add the magnetic field, and you cannot do that in a superconducting condenser.
Okay.
Capacitors. So there are tricks behind that. We have a preprint in the archive if you want to read the 24 pages of appendices that describe all that. You are certainly welcome.
Okay. Good, so I don't see any urgent question anymore, so then I would close the morning session and let's thank both speakers again.